Hello, welcome to my Pipeline Integrity video series. My name is Colin Scott. I'm a pipeline integrity engineer based out of Calgary, Alberta, up in Canada. Today I'm going to be talking to you about the square root of the remaining ligament. And for most of you, this is probably kind of an unusual topic. You're probably wondering why anybody would care what the square root of the remaining ligament was. So I'm going to have to show you. Here I've got a very simple plot. On the y-axis I've got the remaining strength of some corrosion flaws that were failed in a hydro test in the laboratory. And on the x-axis I have the flaw depth ratio, where I've got the corrosion flaw depth divided by the wall thickness. Now each one of those blue rectangles you see represents an actual true real-world data failure strength in a laboratory hydro test. About half of this data comes from Dwayne Cronin's doctoral thesis from the University of Waterloo in 2000, and about half of the data comes from the Pipeline Research Council of the American Gas Association 5th Symposium on Line Pipe back in 1974. So I've got about, I think it's 85 data points. Now, for most of you that are familiar with ASME B31G or any of the other NG18-based failure pressure models, you would expect that if you were to have a very long corrosion flaw, you would expect that the remaining strength would be proportional to the remaining ligament thickness. So the more depth you lose from your corrosion, the thinner the remaining wall, and therefore the proportionality of that remaining strength should match that thinner remaining wall. Now, that's represented by that red dashed line there, the NG18 long corrosion flaw. Now what you'll see is that none of our data points actually approach that. All of our data points are actually above the green dashed line. The green dashed line there represents the square root of that remaining ligament thickness. So although it sounds fairly counterintuitive, it appears from this real-world data, from these 85 data points, that the remaining strength of the corrosion flaws is not proportional to the remaining ligament thickness. It's proportional, or it trends towards, the square root of the remaining ligament. That's a tricky thing to wrap your head around, and so I'm going to show you what my rationale is for that working out that way. Some of you might be familiar with some of my previous videos where I developed something which I call the gamma exponent model, or it's nicknamed the GEM. Here I'm going to show you the very simplified form which I use for metal loss or corrosion flaws. We have a remaining strength, which is equal to the predicted failure strength over the flow strength, and that's equal to 1 minus A over T, all to the gamma exponent. A over T, which we saw just a moment ago, is the flaw depth ratio, so the flaw depth divided by the wall thickness, and so that 1 minus A over T represents the remaining ligament thickness, and all of that is to the gamma exponent. Now the gamma exponent here is defined as the minimum of the length of the corrosion flaw over the radius of the pipe, but up to a maximum of 1/2. And that 1/2 is a very interesting thing. What that 1/2 means is that if we have a long flaw that we're assessing using the gamma exponent model, we would actually see that the remaining strength converges to the proportionality of the square root of the remaining ligament, rather than the actual remaining ligament itself. And that seems a little bit tricky, and it's tricky to wrap your head around, but as we saw in the plot before, that's what the data seems to show. So I'm going to give you a bit of a rationale on why I think that that's happening, though I will tell you right now that this is a work in progress. I haven't got all the little details buttoned down, but I'll show you where I'm at right now. So first we're going to look at the derivation of the gamma exponent model. It was actually originally derived for a crack-like flaw, and so what we're going to do is we're going to think about a crack-like flaw, and then later on in the discussion we're going to think about how things might change for a blunt crack, and therefore how things might change for a corrosion flaw. So right now we're going to look at the wall thickness that we've got here. We have a part-through wall crack of depth A. At the end of that part-through wall crack, we have a small zone which we call the plastic zone, and then we have a remaining ligament, an elastic ligament after that. Now, if you look back at the history of fracture mechanics model development, you'll come across something called the strip yield model. The strip yield model was developed in the 1960s by a couple of fellows named Barenblatt and Dugdale. Now what they did is they came up with a way to approximate elastic plastic behavior using linear elastic fraction mechanics. And what I'm going to do is going to follow that pretty much. Some of you will also know that in the late 1960s and early 1970s, the strip yield model was used to derive the original log secant model that some of you will be familiar with. What I'm going to do a little bit differently here, though, and this is really the heart and soul of the GEM methodology, is to redo that strip yield model and redo the log secant model, but using a part through wall methodology rather than the original work that was done using through wall cracks. So it's a little bit of a twist on your mind, and hopefully you can follow things along. If you're familiar with the strip yield model and derivation of the original log secant model, you're going to be several steps ahead. This can get mathematically a little bit, it's got some twists and turns. So what we're going to do is we're going to think about what is the stress intensity that is acting at the tip of the plastic zone, not the tip of the crack, but the tip of the plastic zone. There are two ways to think about this. And the first one is to see what is the stress intensity factor that is causing opening of that crack and plastic zone. So here I've got a fairly simple fracture mechanics equation where I say that the stress intensity factor to open up that crack and plastic zone is equal to 1.12 times the applied stress times the square root of pi times the crack depth including the plastic zone, and then I have a square root secant term. Now, those of you familiar with fracture mechanics will know that the 1.12 factor is associated with an edge crack. That one's not too difficult to wrap your head around. The trickier one to wrap your head around is the square root secant term. And this is what's called a back wall correction factor. It takes into account that as your crack gets closer and closer to the back wall of the pipe, whether you be coming from the internal or external, there's actually going to be a magnification of the stress intensity factor. So what I've done here is I've included that term, and that all comes down to the crack depth including the plastic zone, remember, because we're looking at the stress intensity at the tip of the plastic zone, and divided by the wall thickness of the pipe. So hopefully that makes a little bit of sense. Now the other option that we can look at in the strip yield solution and figuring out stress intensity factors is we can say to ourselves that within that plastic zone, we know that there is what we'll call a closing stress acting on that plastic zone, which is going to be approximated as being equal to the yield strength of the material. So what we're going to do is we're going to come up with a second stress intensity factor, the closing stress intensity factor, equal to 1.12 times the yield strength in this case, rather than the applied stress. And then we've got square root of pi times the plastic zone depth, and then we have a secant term as well. The secant term also represents the back wall correction factor, but in this case, we're not looking at the full wall thickness. We're looking at the wall thickness minus the crack depth, and we're doing that in terms of the plastic zone depth. Now, according to the strip yield solution and according to sort of fracture mechanics principles, in order to figure out the sort of plastic zone factor associated with the strip yield model, we have to equate those two. K open and K close have to be equal in order to neutralize the stress singularity at the plastic zone tip. So let's do that. Let's equate. Here we equate the two terms. The 1.12 factors fall out. The pi factors fall out, and here we end up with this rather large and ungainly equality. Now what we're going to do is we're going to square those terms and we're going to shift things around, because what we want to do is we want to figure out the ratio of the plastic zone to the crack depth plus the plastic zone. That's how we do the strip yield models. So we end up landing in this little place, and it's kind of a strange thing to wrap your head around. Now what you'll see is we have two secant terms, and it's kind of hard to figure out what we're going to do with those secant terms, but they turn out to be very, very important. So what I'm going to do is I'm going to separate out those two secant terms, and I'm going to figure out what can we do to find a better mathematical relationship that will allow us to kind of subtract the whole plastic zone out of the equation, just like we would with the strip yield model. The first thing I'm going to do is I'm going to take these two terms and I'm going to flip them on their head, and I'm going to change the secants into cosines. So I think that that's fairly easy to do. And the second thing I'm going to do is I'm going to go back to our schematic, and I'm going to say to ourselves, across the wall thickness here, we have a crack depth, we have a plastic zone, and we also have an elastic ligament. Now, if you think about it, if we have a very, very high yield strength, or we have a very, very brittle material, we're going to have a very, very small plastic zone, and we're going to have a longer, relatively speaking, a longer elastic ligament. However, if we're in a situation where we have a very high tough material, and we have a situation where we've got a very low yield strength, then we're going to expect to get a much, much deeper plastic zone, which is mean that we're going to have actually a much, much smaller elastic ligament. And that's really key to this whole thing. If we have a lot of ductility at the crack tip, if we have a lot of yielding through that elastic ligament, we're going to blunt our crack, and we're going to be able to simulate a metal loss flaw or a corrosion flaw. And that's a very, very important thing. It's very important to think that our elastic ligament is going to get very, very small during a ductile failure or a plastic collapse type solution. What I'm going to do here is I'm now going to take advantage of that work that we learned back in probably in high school, where we say cosine of x is equal to sine of pi over 2 minus x. And that really comes down to just the cosine and sine curves are shifted in space by that pi over 2 factor. So what I'm going to do here is I'm going to take advantage of that little relationship. And when I do that, I can get my ratio here in terms of sine rather than cosine. And I can also get things in terms of the elastic ligament depth. So that's what I've done there. The second thing I'm going to do is I'm going to take advantage of that old rule that we also learned in high school or college, where we say sine x is equal to x if we have a very small x. So here I've got a plot of a simple sine curve, and you can see if you're right there near x equals 0, give or take about 0.5 radians, you actually have a linear relationship there. It's basically a one-to-one relationship. So if you have an angle there that's small enough, you can basically get away with saying sine x is equal to x. Now, I've already specified that if we're thinking about a ductile material and we've got low yield strength and we've blunted our crack and we have a large plastic zone, our elastic ligament is going to get smaller and smaller and smaller. So I propose that because our elastic ligament is smaller within this particular scenario, because we're looking at blunt flaws, because we're looking at ductility, because we're looking at deep plastic zones, we should be able to use this relationship to effect. It turns out that accomplishes quite a lot. You see that our sine over sine ratio has now turned into, at the end of the day, t over t minus a. So that's the wall thickness divided by the wall thickness minus the crack depth. Now, if you think hard, that's actually the inverse of the remaining ligament. It's 1 over the remaining ligament. And that's a very interesting thing, and that's really quite a fascinating coincidence to me that the mathematics plays out this way. Now, things get even better, because I think I told you before that the model predicts that we're going to have a proportionality to the square root of the remaining ligament rather than the remaining ligament itself. So let's see how that plays out. First, what we're going to do is we're going to take that t over t minus a term and we're going to plug it right back into the equation that we saw a few slides ago. So basically, we are replacing that secant over secant term. And that gets us an expression which describes the ratio of the plastic zone depth to the flaw depth plus plastic zone. Now, in order to follow the strip yield model solution and look at the way the log secant was developed, what we actually want to do is we want to find out what's the relationship of the flaw depth to the flaw depth and plastic zone. So we go through the simple, 1 minus sigma applied squared over sigma yield squared times that t over t minus a factor. Hopefully that follows. It really just means juggling the terms around a little bit. Now we're going to go back to some more theory that we might have seen in high school, probably more likely saw in college, because it's got something to do with those crazy Fourier series expansions and stuff like that, where if you have a situation where you have y equals 1 minus x squared, which here we've got shown by the green curve. You can see it's a downward pointing curve. That looks an awful lot like a cosine curve. So the red curve gives us y equals cosine of pi over 2 times x. And you can see from just visually that those two equations are mathematically very, very similar to each other. Now, a key thing is, if you take your green curve and shift it to the red curve, you are taking your x squared term and you are actually square rooting it to put it into the cosine term. So that gets to be very interesting and turns out to be quite the coincidence. Because when we go through the math, just like we would with the strip yield solution and trying to come up with a log secant model, we've taken that t over t minus a term and we've square rooted it. That's a very interesting thing. As we keep going with the math, we realize that we can take this whole term and we can insert it back into our k opening equation. Now, I mentioned before that this is kind of a work in progress. I haven't buttoned down everything, but it's kind of an interesting way that the math plays out. So here's my k open term, which is exactly the same as it was before. But what I've done is I've taken that a plus rho, the crack depth plus plastic zone depth, and I've turned that into the a times secant term that we just derived. And that a times secant term includes the square root of the inverse of the remaining ligament. Now, those of you that are really familiar with your fracture mechanics and particularly observant will notice that this equation should also have another square root of secant term. So I've got that term here in kind of grayed out because, to be honest, I'm not sure exactly how to resolve that. I went through the original derivation of the gamma exponent model. I wasn't quite sure what to do with that second secant term, and so I decided to just gently put it aside and back calculate what the gamma exponent model was empirically. And things seem to work. Now, if you're familiar with my gamma exponent model, I will say that if you have a crack-like flaw, you're going to maximize your gamma exponent at 1, but if you have a corrosion flaw, a metal loss flaw, you're going to limit your gamma exponent to 1/2. So essentially what I've done here is I've shown you where that 1/2 term comes from, and that all comes down to working through the math and assuming that you've got a lot of plastic zone, you've got a lot of ductility in your material, you're kind of like in a plastic collapse situation, and you've got a very small elastic ligament. And you can see that that elastic ligament makes the math work out fairly nicely. Now, hypothetically speaking, if you kept going with this basic equation, you would find yourself in a situation that looked very much like the log secant model. It would look very much like my full gem model for crack-like. And what you have to do there is you have to say to yourself, in the hypothetical situation that we're looking at a blunt crack and we have a lot of ductility, we're actually going to find ourselves in a plane stress scenario. And in that situation, we're going to want to use a plane stress toughness, which actually causes the fracture term in the equation to kind of self-eliminate. And what we end up doing is landing just on the proportionality of the remaining strength the remaining strength being proportional to the square root of the remaining ligament. Now, as far as that spare sec term works out, I haven't quite figured that one out. It seems to me that that is coming into play a lot more with the crack-like flaws than the corrosion flaws. And like I said, work in progress, which I'm working on. But you'll see from the math that I've shown you that it's kind of an interesting coincidence that you do end up finding that square root relationship. Now, I've used the basic model that I showed you before for metal loss, and I've come up with a level 2 analysis, which I call the ELM. It's the equivalent length method analysis. And when I apply that to the profiles that I've got, of all the data points that I showed you before, I have about 23 profiles that are in the Dwayne Crone and doctoral thesis from 2000. If I apply my level 2 analysis to those 23 profiles, I actually get very, very good agreement between the predicted failure strengths using the simplified gem model and using the true failure strengths that were measured in the lab. I think you'll find that agreement is quite a bit better than any of the B31G models, including R-Strang, and actually including the more recently developed P-squared model. Now, Like I said, I've got a spare secant term that I'm not sure quite how it all fits in. I still have to resolve that, but what I can see so far is that square root relationship seems to be very effective, because that square root relationship is built into this Elm model, the GEMS Elm model. So things seem to be pointing in the right direction. For anybody that's interested in further pipeline integrity videos, I do have a series of videos on YouTube that you can find fairly easily. Probably the most interesting one for some of you will be pipeline integrity, things that make me go, parts 1 to 6. Those are really a critique of the original NG18 Battelle work that was done in the late 1960s and early 70s. I think that back then the group made a couple of bad assumptions regarding the way length and depth are handled, and I think that industry should have a good hard look at that situation and see what can be done to resolve the situation, as well as looking at the derivation of my GEM model, which I think solves some of the theoretical problems from 50 years ago. I've also got some validation work from the gamma exponent model. I've shown that the gamma exponent model can be kind of twisted and turned around and turned into a failure assessment diagram type model if you like that. And I can also do some leak rupture boundary work as well. For those of you that are looking for more authentic real publications, I do have one paper through NACE. There's another on the way, and I have 2 papers through ASME. The bottom of these papers, ASME Journal of Pressure Vessel Technology, gives more of the mathematical details behind the development of the gamma exponent model. For those of you that made it this far, thank you very much. I appreciate your time. I know that some of this mathematics is a little bit complicated, and I know that I've made a few simplifications and assumptions along the way that will have some of you up in arms. I will say that the core idea that the square root of the remaining ligament does actually come out of the derivation, I think, is a very important one. It might be somewhat unnatural to think of things that way, but so far the mathematics seems to be working. I'm going to continue to try and figure out some of those loose ends, like that spare secant term, and hopefully I can give you an update sometime soon where I've got some more of the math buttoned down. Hopefully you followed this some of the way along the way, and hopefully that gives you some things to think about. Until next time, thank you very much for your time.